Introduction to Chromatography. Chromatography is a separation technique based on the different interaction of compounds with two phases, a mobile phase and a stationary phase, as the compounds travel through a supporting medium. This is a technique in which the components of a mixture are separated based on the difference in the rates at which they are carried through a fixed or stationary phase by a gaseous or liquid mobile phase. The components of chromatography are the mobile phase, the stationary phase, and the supporting medium. For mobile phase, it is a solvent that flows through the supporting medium. It can be gas, liquid, or supercritical fluid. For stationary phase, it is a layer or coating on the supporting medium that interacts with the analytes. This is fixed in place. The supporting medium, this is a solid surface on which the stationary phase is bound or coated. So here are the classification of chromatographic methods based depending on the type of support material, the mobile phase, and the stationary phase. So first, based on the type of support material. So under this type is first is the column chromatography, where the stationary phase is held in a narrow tube, while the mobile phase is forced through the tube under pressure or by gravity. So an example or a picture of column chromatography is this. So as you can see, there is a tube, and inside the tube is the sorbent or the stationary phase, and the mobile phase will be added at the top of the tube. Second is the planar chromatography. So the stationary phase is supported on a flat plate or in the pores of a paper, while the mobile phase moves through the stationary phase by capillary action or under the influence of gravity. So an example of a planar chromatography is the paper chromatography. So here is the picture for paper chromatography. Okay, the next classification is based on the nature of the mobile phase. So it can be gas, liquid, or supercritical fluid. So when the mobile phase is gas, it is called gas chromatography or GC. So if the mobile phase is liquid, it is called the liquid chromatography or LC. And when the mobile phase is supercritical fluid, it is called supercritical fluid chromatography or SFC. So last is based on the stationary phase. So for gas chromatography, where the mobile phase is gas, um, the name of GC method, so for gas solid chromatography, the type of stationary phase is solid. For gas liquid chromatography, the type of stationary phase is liquid. So for liquid chrome, if it is adsorption chromatography, the stationary phase is solid. For partition chrome, the stationary phase is liquid, and for ion exchange chromatography, the supporting material contains fixed charges. For size exclusion chrome, there is a porous support. For affinity chrome, the support has immobilized ligand. So here are the block diagram of gas chrome and liquid chromatography. So for gas chrome, in the carrier gas are the mobile phase. Okay, so here is the column inside the column oven, and then here in the injector port is where you inject your sample. But karon sa modern na um, mga instrument for gas from dili na necessary or wala na siya injector port because we use a auto sampler na, so dili na ga-inject sa sample. Same with the liquid chromatography. So for liquid chrome, here is the column, and um, the sample and the mobile phase is passed through the column, then the detector, or same with the group GC, naapod ni siya detector diri, also for LC, then the recorder, and then the result. Illusion in chromatography. So here are the different words for illusion in chromatography. So the word illusion, it is the process in which the solutes are washed through a stationary phase by the movement of a mobile phase. While the illuate, it is the mobile phase that exits the column. And the illuent, it is the solvent used to carry the components of a mixture through a stationary phase. So those are the difference between those three words: illusion, illuate, and illuent. So here is an example kung unsay gakahitabo sa illusion sa chromatography. So at T sub 0, a solution of the sample containing a mixture of A and B in a mobile phase is introduced at the head of the column. So for example, this is a crude sample, crude plant extract. So sa crude nga sample, you have different compounds pa. So for example, diri na ay compound A and compound B, and you want to separate them. So at T sub 1 and T sub 2, so at T sub 1, nagbutang ka or first introduction of your mobile phase. So in T sub 2, further introduction of mobile phase. So the portion of the sample in the mobile phase moves down the column. So niadto na siya sa ubos. So we're further partitioning between the mobile phase and the stationary phase occurs. So the average rate at which the solute migrates depends on the fraction of time it spends in the mobile phase. Analytes interacting most strongly, which is B, so ga-interact siya more sa stationary phase, will take longer to pass through the system than those with weaker interaction of the stationary phase, which is compound A. So the resulting difference in rates cause the components in a mixture to separate into bands or zones along the lengths of the column. So meaning si B, which is ga-interact siya more sa stationary phase, mas dugay gid siya mogawas kaysa si A nga mas weaker iyahang interaction with the stationary phase inside the column. So kanang difference nila sa ilang rate sa paggawas sa column, mao na dayon na siya ang ginadetect. So at T3 and T4, individual bands eluted from the column where they can be collected or detected. So at T3, si A ang nigawas. So this is illuate A, and this is illuate B. So here is an example of a chromatogram. So we will discuss it more later. Okay, here. Chromatogram. It is a plot of concentration versus illusion time or illusion volume. The position of the peak maxima on the time axis can be used to identify the components of the sample. Peak areas provide a quantitative measure of the amount of each species. So the effect of relative migration rate. So when A is more strongly retained by the stationary phase than B, B lags during the migration. So as you can see in the chromatogram, so meaning CB must um, CB, so for a chromatogram, C0 times 0 is diri nga axis. Okay? So, kay si B man ang mas una nga nigawas sa column, meaning si B mas less iyang interaction with the stationary phase, and A is more strongly retained by DSP. So B lags during the migration. So distance between A and B increases as they move down the column. Broadening of both bands takes place also. So the broadening ato nang ma-discuss later. So two methods of improving separation: increase the rate of band separation and decrease the rate of band spreading. Variables that influence relative migration rate of solute. So the effectiveness of a chromatographic column in separating two solutes depends on part on the relative rates at which the two species are eluted. Rates are determined by the ratios of the solute concentration in each of the two phases. So the distribution constant or the partition law ratios. So the chromatographic separation are based on differences in the extent to which solutes are distributed between the mobile and the stationary phase. So we have tackled this already in our past discussion. So the ideally distribution constant or K is constant over a wide range of solute concentration. That is, CS is directly proportional to Cm. So first variable that influence the relative migration rate of solute is the retention time. So Tm, where it is the dead or void time, is the time it takes for an unretained species to pass through a chromatographic column. So mo ni si Tm. So kung maggamit mo og chromatography nga instrument, kanang first nga mogawas nga peak dili pa na siya mao imong analyte. That is called dead time or void time. So, si TM, mauna siya ang mga unretained species nga naadaan sa or ga-pass through first sa chromatographic column. Then, separations are based on the different times or TS that components spend in the stationary phase. While the TR or the retention time is the time required for the analyte peak to reach the detector after sample injection. Okay. Retention factor are capacity factor denoted by small letter K. So it is an experimental parameter widely used to compare the migration rates of solutes on columns, the amount of time a solute spends in the stationary phase relative to the time it spends in the mobile phase. So for solute A, the retention factor is expressed like this. So when Ka is less than 1, solute emerges from the column at a time near the void time or the dead time. So for when Ka is greater than 20 to 30, illusion times become inordinately long. So taas na sad kaayo. But when Ka is less than or equal to 1 and greater than or equal to 5, it is an ideal separation. Next is the selectivity factor or small letter A. So it provides a measure on how well a column separates two analytes. This is the ratio of the partition ratio of a more strongly retained solute to the partition ratio of the less strongly held solute. So for two species A and B, mao ni siya ang iyahang selectivity factor, where Kb is the partition ratio of more strongly retained species, which is B, and the Ka is the partition ratio of less strongly held or more rapidly eluted species, which is A. Can also be expressed as Kb, small letter Kb, and Ka, where Kb is the retention factor for B and Ka is the retention factor for A. So to determine A from the chromatogram, you can use this equation. Band broadening and column efficiency. The amount of band broadening that occurs as a solute passes through a chromatographic column strongly affects the column efficiency. The rate theory of chromatography, it describes the shapes and the breadths of illusion bands in quantitative terms. Illusion peaks looks very much like the Gaussian or normal curve and normal error curves. As a single solute molecule undergoes many thousands of transfers between the stationary and the mobile phases during illusion, residence in time in either phase is highly irregular. The transfer from one phase to the other requires energy, and the molecule must acquire this energy from its surrounding. Residence time in a given phase may be very short after some transfers and relatively long after others. The movement through the column can occur only while the molecule is in the mobile phase. Certain particles travel rapidly by virtue of their accidental inclusion in the mobile phase for a majority of the time, and other particles lag because they may be incorporated in the stationary phase for a greater than average length of time, results to a symmetric spread of velocities around the mean value. So this represents the behavior of the average analyte molecule. Band broadening. Some chromatographic peaks are non-ideal and exhibit tailing or fronting. So tailing and fronting are undesirable because they lead to poorer separations and less reproducible illusion time. So tailing can be due to distribution constant that varies with concentration. Also for fronting, and fronting is the introduction of large amount of samples onto a column. So kung dako pud kayo imuhang isulod or i-run sa imuhang column, mag-result sad siya og fronting. Quantitative description of column efficiency. Efficiency is related experimentally to a solute's peak width. So an efficient system will produce very narrow peaks. So narrow peaks means smaller difference in interactions in order to separate two solutes. Efficiency is also related theoretically to the various kinetic processes that are involved in solute retention and transport in the column. So these determine the width or the standard deviation of peaks. Quantitative measures of chromatographic column efficiency is used magamit siya og plate height or H, aka height equivalence of a theoretical plate or HETP, and the plate count or the number of theoretical plates, which is N. So N is equal to L over H, where L is the length in centimeters of the column packing. So the column efficiency increases when H becomes smaller, therefore N increases. So the differences in efficiencies are encountered in columns due to differences in column type. So the mobile phase nga gigamit and the stationary phase nga gigamit. N can be determined, so N can be determined from a chromatogram. The retention time of a peak, the TR, and the width of the peak at its base, or this W, in units of time are measured. So the larger the value of N is for a column, the better the column will be able to separate two compounds. The better the ability to resolve the solutes that have small differences in retention. And N is independent of a solute retention, but N is dependent on the length of the column. Okay, next is the effect of mobile phase flow rate. Efficiency studies have been carried out by determining H as a function of mobile phase velocity. So for GC and LC, shows a minimum in H, meaning a maximum efficiency at low linear flow rates. Then the minimum for LC usually occurs at flow rates well below those for GC. So mas bubo dapat ang or mas better si LC, mas taas iyang efficiency ni LC kung mubo iyahang flow rates than those for GC, gas chrom. Okay, liquid chromatograms are obtained at lower linear flow rates than gas chromatograms. LC columns are more smaller than those with GC columns. So It is impractical to use LC columns that are longer than about 25 to 50 centimeters because of high pressure drops. But for GC columns, so meaning ang LC, ang column sa liquid chrome is mubo siya than 25 centimeters. But for GC columns, it can be 50 meters or more in length. The total number of plates and overall column efficiency are usually superior with GC columns. Longitudinal diffusion term. This results in the migration of a solute from the concentrated center of a band to the more dilute regions on either side, that is, toward and opposed to the direction of flow. This is a common source of band broadening in gas chrome than in liquid chrome where the rate at which molecules diffuse is high. The contribution of longitudinal diffusion to plate height is inversely proportional to the linear velocity of the eluate. In this situation, the analyte is in the column for a briefer period when the flow rate is high. Next is the stationary phase mass transfer term. This is the band broadening due to the movement of solute between the stagnant phase and the stationary phase. Since different solute molecules spend different lengths of time in the stationary phase, they also spend different amounts of time on the column, giving rise to band broadening. The degree of band broadening due to stationary phase mass transfer depends on the retention and diffusion of the solute, the flow rate of the solute through the column, and the kinetics of interaction between the solute and the stationary phase. So when the stationary phase is an immobilized liquid, kung ang stationary phase is immobilized liquid, the mass transfer coefficient is directly proportional to the square of the thickness of the film on the support particles, or dF squared. And it is inversely proportional to the diffusion coefficient, or ds, of the solute in the film. So the dF2 and the ds reduce the average frequency at which the analyte molecules reach the interface where transfer to the mobile phase can occur. So with thick films, molecules travel farther to reach the surface. With smaller diffusion coefficient, molecules travel, travel slower. So the result is a slower rate of mass transfer and an increase in plate height. So when the stationary phase is a solid surface, the mass transfer coefficient is directly proportional to the time required for a species to be adsorbed or desorbed. The next is the mobile phase mass transfer term. So the mobile phase mass transfer coefficient, or Cm, is inversely proportional to the diffusion coefficient of the analyte in the mobile phase, or dm. So first is the eddy diffusion. It is a process that leads to peak or band broadening due to the presence of multiple flow paths through a packed column. So as solute molecules travel through the column, some arrive at the end sooner than others simply due to the different path traveled around the support particles in the column that result in different travel. So for example, in this picture, si 1, lahi siya og path nga agian kaysa kang 2. So, makita ninyo, mas difficult ang path nga giagian ni 2. So, mas dali gid nga moabot si 1 compare kang 2. So, mao na ang pasabot sa eddy diffusion. So, longer paths arrive at end of column after 1. Mas una gid si 1. So, the different residence times in the column for molecules of the same species vary. So, another example or kani nga picture, so same sila nagsugod, but because pag agi sa column lahi-lahi sila paths, so mas katong pinakasayon og path mas una gyud siya moabot compare atong difficult iyahang path nga agian. Okay, so the next is the stagnant mobile phase mass transfer. So this is the band broadening due to differences in the rate of diffusion of the solute molecules between the mobile phase outside the pores of the support or the flowing mobile phase to the mobile phase within the pores of the support or the stagnant mobile phase. So since a solute does not travel down the column when it is in the stagnant mobile phase, it spends a longer time in the column than solute that remains in the flowing mobile phase. So the degree of band broadening due to stagnant mobile phase mass transfer depends on the size, shape, and pore structure of the packing material. So katong sorbent nga um, sulod sa column. So, ang size, ang shape, ug ang pore. Next is the diffusion and the retention of the solute and the flow rate of the solute through the column. Next is the mobile phase mass transfer. So, it is a process of peak broadening or band broadening caused by the presence of different flow profile within channels or between particles of the support in the column. So a solute in the center of the channel moves more quickly than solute at the edges. It will tend to reach the end of the channel first, leading to band broadening. So, of course, it is given na for those who solute nga naa sa tunga mo agi, mas paspas siya compare sa edges siya mo agi. So, it will lead to band broadening. So, the degree of band broadening due to eddy diffusion and mobile phase mass transfer depends mainly on the size of the packing material and the diffusion rate of the solute. So here is the Van Dimter equation. It relates the flow rate or linear velocity to h, where h is equal to a plus b over mu plus c mu, where mu is the linear velocity or the flow rate times Vm over L. H is the total plate height of the column. A is the constant representing eddy diffusion and mobile phase mass transfer. B is the constant representing longitudinal diffusion, and C is the constant representing stagnant mobile phase and stationary phase mass transfer. So one use of plate height is to relate this kinetic process to band broadening to a parameter of the chromatographic system. So example is flow rate. This relationship is used to predict what the resulting effect would be of varying this parameter on the overall efficiency of the chromatographic system. So there is an optimum flow rate at which the plate height is a minimum and the separation efficiency is a maximum. So the summary of methods for reducing band broadening are: decrease the particle size and the column diameter. Next is, with gaseous mobile phases, the rate of longitudinal diffusion can be reduced appreciably by lowering the temperature, meaning it lowers the diffusion coefficient. Thirdly, with liquid stationary phases, the thickness of the layer of adsorbed liquid should be minimized. Column resolution or RS. So the resolution between two peaks is a second measure of how well two peaks are represented. So RS can be calculated or using this equation. So RS is preferred over a since both retention and column efficiency. Okay, RS is preferred over A since both retention, column resolution or RS. So resolution between two peaks is a second measure of how well two peaks are separated. RS is given by this equation. So RS is preferred over A since both retention time and column efficiency are considered in defining peak separation. So when Rs is equal to 1.5, it gives an essentially complete separation of A and B. But when Rs is equal to 0.75, it gives poor separation. So band broadening siya or overlap sila. For Rs equal to 1, the zone A contains 4% B and zone B contains about 4% of A. So at Rs 1.5, the overlap is about 0.3%. So for a given stationary phase, the Rs for a given stationary phase can be improved by lengthening the column, thus increasing the number of plates. The added plates, however, result in an increase in the time required for separation. Optimization techniques. First is the variation in plate height. The resolution of a column improves as the square root of the number of plates increases. So meaning, kung patason or padaghanon nimo ang number of plates, mo improve pod ang resolution sa column. However, increasing the number of plates is expensive in terms of time, unless the increase is achieved by reducing the plate height and not by increasing the column length. So, kung i-increase po di ay ang number of plates, kinahanglan po siya or ga-require siya og mas taas nga time. Unless, kung i-increase nimo ang number of plates, imuhang i-reduce ang plate height ug dili nimo i-increase ang column length. So the ways to minimize plate height is by reducing the particle size of the packing material, the diameter of the column, and the thickness of the liquid film, and optimize the flow rate of the mobile phase. Next, or number two, is the variation in the retention factor. So, increases in KB generally enhances resolution. Kung imong patason si KB, mas taas pod ang resolution, but at the expensive of illusion time. Again, so values of KB is which is greater than 10, it provide little increase in resolution but markedly increase the time required for separation. So need gyapon, so kung i-increase pud nimo si KB, need pud nimo og or required mag-require sad siya og mas taas nga time. So optimal values of KB lies in the range from 1 to 5. So mas better or it is optimal na ang value sa KB naa siya sa 1 to 5. For gaseous mobile phases, K can often be improved by temperature changes, and for liquid mobile phases, changes in the solvent composition optimizes K to yield better separation. Next is the variation in selectivity factor. Optimizing K and increasing N are not sufficient to give a satisfactory separation of two solutes in a reasonable time when A approaches to 1. So increase A while maintaining K in the range of 1 to 10. So options are changing the composition of the mobile phase, changing the column temperature, changing the composition of the stationary phase or interchange columns, then using special chemical effects. General illusion problems. So chromatogram A, um, you can see here on the figure, the conditions adjusted so that the retention factors for component 1 and 2 or the K1 and K2 are within the range of 1 to 5. So as you can see in the figure, narrow ilahang peaks because their retention factors are within the range of 1 to 5. For the factors, for the other components are far larger than the optimum. So bands corresponding to component 5 and 6 are broad and appear only after an inordinate length of time has passed. So as you can see, si 6 ang pinaka-last nga nakagawa sa column and broad na pagyud ilaha nga band together with component 5. In chromatogram B, changing conditions to optimize the separation of components 5 and 6 bunches the peaks of the first four components to the point where their resolution is unsatisfactory. The total illusion time is ideal. So for chromatogram A, makita ninyo nga taas nga time iyaha nga gi-require. But for chromatogram B, short ra, yes, the total illusion time is ideal. How para iyahang ma-separate og ayo si 5 and 6. However, for compound 3, 4, and 1 and 2, their resolution is very low nga nag-lead sa ilaha to overlap. So those are the common problems you can encounter in chromatography. For the solution, we can change or you can change the conditions stepwise that determine the values of K as the separation proceeds. So for liquid chrome, variation in K are brought about by varying the composition of the mobile phase during the elution, meaning the gradient elution or the solvent programming. For isocratic illusion, also illusion under conditions of constant mobile phase composition. Meaning sa isocratic illusion is one lang gid imong gamiton nga mobile phase throughout the analysis. So for gas chrom, the temperature can be changed in a known fashion to bring about the changes in K. So the temperature ang imuha nga i-change. So temperature programming mode. So application for chromatography. For qualitative analysis, it is used for recognizing the presence or absence of components in mixtures that contain a limited number of species whose identities are known based on retention time. So, pwede na to ma-recognize or pwede na to mahibalaan ang kung present ba siya or absent sa ato ang sample uh, based sa retention time na mahatag sa chromatogram. So that is for qualitative analysis. And then confirmation of identity would require spectral or chemical investigation for isolated components. The chromatogram may not lead to positive identification of the species in the samples, but it often provides sure evidence of the absence of species. So chromatograms possible siya nga dili gyud maghatag siya og positive identification like kanang kana na gyud siya mao na gyud ni siya nga so for example kani nga peak kana na gyud ang atong sample nga gipangita so dili gyud siya inana but then it can provide sure evidence kung absent na siya nga species. So failure of a sample to produce peak at the same retention time as a standard obtained under identical conditions is strong evidence that the compound in question is absent or present at a concentration below the detection limit of the procedure. For example, magranta og standard, then magranta og sample. So, same silang condition giran. But then, pag abot sa sample nato or sa atong crude sample, wala ni gawas ang peak kung aha ni gawas ang peak sa standard. Therefore, ato siyang, it is a strong evidence. Pwede na siya nga very sure evidence and strong evidence that the compound in question is absent. So that is for qualitative analysis. For quantitative analysis application of chromatography, it is based upon a comparison of either the peak height or the peak area of the analyte with that of one or more standards. So we need a standard. Analysis based on peak height can be used provided variations in column conditions do not alter peak widths during recording of chromatograms. Peaks should not be distorted or the column overloaded. So analysis based on peak area is less sensitive to small changes in operating conditions. It is independent of broadening effects. For calibration with standards, so first is the external standard method. It involves the preparation of a series of standard solutions that approximate the composition of the unknown. The calibration is a plot of peak height or peak area versus concentration of standard. So that is for external standard method. For internal standard method, it minimizes uncertainty in sample injection and variability due to instrument conditions. A careful measured quantity of an internal standard is introduced into each standard and sample, and the ratio of the analyte peak area or peak height to internal standard peak area or peak height is obtained. The calibration curve is a plot of the ratio versus concentration. The requirements for internal standard, it must be completely resolved, must elute near peaks of interest and similar in concentration to peaks of interest, and it should be chemically inert and absent in the sample. So that's the end for the introduction for chromatography.